Stellar black holes. Let me start by taking you to the most violent places in the cosmos. Picture a star, not just any star, but one of those absolute behemoths, at least 20 times more massive than our own sun. When the fuel finally runs out, there's no gradual wind down. The star's core collapses in on itself in less than a second. We're talking about a core the size of a city, literally thousands of kilometers across, compressing down to just a few dozen kilometers. During this gravitational collapse, every fundamental force in the universe becomes completely powerless. The electromagnetic force that holds atoms together? Meaningless. The strong nuclear force binding protons and neutrons? Useless. Gravity wins, and it wins so decisively that it creates something that fundamentally breaks our normal understanding of reality. The matter gets compressed to densities so extreme that a single teaspoon of this stuff would weigh as much as Mount Everest. You could hold the equivalent of an entire mountain in the palm of your hand. This creates an object that typically weighs between 3 and 100 times the mass of our sun, yet fits into a sphere no bigger than a typical city. Imagine taking the entire mass of dozens of suns and squishing it all down to fit inside Manhattan. That's what we're dealing with. Around every one of these stellar black holes sits an invisible boundary called the event horizon, the true point of no return. Beyond this line, nothing can escape. Not matter, not light, not even radiation traveling at 300 million meters per second. It just vanishes into an abyss. For a stellar black hole with 10 times the mass of the sun, this event horizon would be roughly 30 kilometers across. Small doesn't mean less dangerous, though. Here's where it gets truly horrifying. If a stellar black hole exists near a companion star, it starts feeding like a cosmic vampire. The stolen gas spirals inward in a swirling disk called an accretion disk. Friction heats it to millions of degrees, making it glow brilliantly in X-rays. Scientists estimate our Milky Way galaxy alone harbors millions of these stellar black holes. Most are just drifting silently through space, completely invisible, until one passes in front of a distant star and bends the starlight through the gravitational lensing, making the star appear brighter. Rotating Kerr black holes. Most black holes in the universe aren't stationary, they're spinning. Sometimes slowly, sometimes incredibly fast. When you add rotation to a black hole, you're creating one of the most extreme objects possible. Spacetime doesn't just warp, it gets twisted. Spacetime itself is literally dragged around by the black hole's spin in a phenomenon physicists call frame dragging. Imagine the black hole spinning and dragging the fabric of spacetime along with it. It's like stirring honey with a spoon, except the honey is space and time itself. This creates absolutely bizarre physics. Objects experience forces that don't exist anywhere else in the universe. What makes rotating black holes particularly dangerous is their ability to extract energy. Unlike non-rotating black holes, which just swallow everything, rotating black holes can be thought of like cosmic power plants. Charged particles get trapped in the intense magnetic fields surrounding the black hole, and these fields fling the particles outward along the rotation axis at nearly the speed of light. These jets can extend for millions of miles into space, releasing energy comparable to millions of supernovae. The mathematics becomes almost impossibly complex when dealing with extremal Kerr black holes, rotating at nearly their maximum rate. Recent theoretical work suggests these extreme rotators might even be sensitive probes of quantum gravity itself, at the edge of physics as we understand it. Intermediate black holes. Stellar black holes weigh between 3 and 100 times the mass of our sun. Supermassive black holes weigh millions or billions of times more. That's an impossibly large gap to bridge through normal processes. Here's what keeps astronomers awake. Supermassive black holes already existed when the universe was less than 1 billion years old. If a stellar black hole tried to grow into a supermassive black hole just by consuming nearby matter, it would take far longer than the entire age of the universe. So, how did these supermassive behemoths get so massive so quickly? The answer might be intermediate black holes. Intermediate black holes would occupy the middle ground, weighing anywhere from a few hundred to roughly 100,000 times the mass of our sun. They could be the crucial missing link explaining how stellar black holes grow into supermassive black holes. But here's the problem. We almost never find them. Why? Because they're absolutely invisible by normal standards. They don't consume vast amounts of matter, so they don't produce the dramatic light shows that make supermassive black holes easy to spot. The only way to find intermediate black holes is by looking for gravitational fingerprints in dense star clusters. An intermediate black hole sitting at the center would influence nearby star orbits. Astronomers map stellar movements, looking for orbital patterns suggesting an invisible, massive object. It's like trying to find an invisible giant in a crowded city by watching how people walk around them. Despite decades of searching, they remain one of the most elusive objects in the universe. Primordial black holes. So black holes don't have to form from collapsed stars. Some black holes might have formed long before the first stars ignited, born in the chaotic moments following the Big Bang itself. These are primordial black holes. In the early universe, just fractions of a second after the Big Bang, extreme density fluctuations could have created tiny, localized regions where gravity was so powerful that they simply collapsed into black holes. These primordial black holes could range from incredibly small all the way up to massive sizes. Some could be asteroid-sized, but compressed down to the size of a hydrogen atom. And if they're small enough, they don't even stick around. Stephen Hawking proved that small black holes actually evaporate through Hawking radiation. The smaller a primordial black hole is, the hotter it is, and the faster it radiates away its mass. Scientists believe there's about a 90% chance that we could actually detect these explosions if they're happening in our solar system or nearby regions of space. What makes primordial black holes genuinely unsettling is that they could actually be the dark matter we've been searching for. About 85% of all matter in the universe is dark matter, stuff we can't see or detect directly. What if a significant fraction is actually primordial black holes? We could have countless tiny black holes just passing through our solar system right now, completely invisible. Recent research confirms that if a primordial black hole passed through your body, it would leave only microscopic tunnels. But a larger one passing through a planet could leave a hollow cavity. Ultramassive catastrophes. Yup, at the centers of most galaxies sits a supermassive black hole. Our own galaxy, the Milky Way, has one called Sagittarius A, weighing about 4.6 million times the mass of our Sun. It's considered modest by cosmic standards, roughly 100,000 times smaller than the largest known supermassive black holes. That's TON 618, and honestly, this black hole breaks the scale of comprehension. TON 618 contains an estimated 66 billion times the mass of our Sun. If you took every single star in the Milky Way, all roughly 200 billion of them, and added up all their mass, you'd still have fewer stars worth of matter than TON 618 contains. The event horizon of TON 618 is about 1,300 astronomical units across. An astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So, TON 618's event horizon spans about 121 billion miles across. That's more than 40 times the distance from Neptune to the Sun. 11 solar systems could fit inside it side by side. Light would take an entire week just to cross from the edge of the event horizon to the singularity at the center. The reason we know TON 618 is so massive comes from its emission lines. The gas is moving at insane speeds, with some measurements showing infalling material traveling at 34 million miles per second. The only way gravity can be strong enough to achieve that is if the black hole is absolutely colossal. The terror of tidal forces. I need to describe something that makes dying in the vacuum of space look pleasant. Spaghettification. This is how physicists actually describe one of the most brutal phenomena in the cosmos. Imagine falling into a black hole feet first. As you get closer, gravity at your feet becomes exponentially stronger than gravity at your head. This differential in gravitational force is called a tidal force, and it literally tears objects apart. For a stellar black hole with 10 times the mass of the Sun, someone falling feet first would experience a tidal acceleration of about 2 billion times Earth's surface gravity by the time they reach the event horizon. Your feet would experience trillions of tons of force beyond what your head experiences. Your body would literally be stretched like spaghetti, elongated vertically while compressed horizontally. You'd be torn apart before even realizing what was happening. Supermassive black holes are different. The event horizon is so enormous that tidal forces right at the event horizon are actually relatively gentle. You could theoretically fall through unaware. Only later, as you spiral deeper toward the singularity, would the tidal forces become deadly. But we've actually observed spaghettification on a galactic scale. When a star gets too close to a supermassive black hole, tidal forces completely shred it. During these tidal disruption events, the entire star is stretched and torn apart. The debris forms into a spaghetti-shaped stream spiraling toward the black hole, with violent jets of material ejected back into space, releasing radiation across the entire electromagnetic spectrum. Black hole collisions. For most of cosmic history, we could only imagine what happened when two black holes collided. Then, in 2015, everything changed. The LIGO gravitational wave detectors picked up the first ever detection of gravitational waves from colliding black holes, opening an entirely new window into understanding these cosmic monsters. When two black holes orbit each other, they gradually spiral inward. As they do, they emit gravitational waves, ripples in spacetime itself. These waves carry away energy and angular momentum, causing the black holes to spiral faster. Eventually, they move at near light speed, orbiting in their final moments before merging. And then it happens. The two event horizons touch and merge. The two black holes become one. In that moment of merger, gravitational waves are emitted with absolutely staggering power. The energy released in these final seconds can exceed the total energy output of all stars in the observable universe combined, released in gravitational radiation. Recent detections revealed something even more startling. In July 2025, LIGO detected the most massive black hole merger ever observed. The two merging black holes had masses too large for physicists to easily explain. These are forbidden mass black holes. They shouldn't exist, yet they definitely do. The universe just keeps getting scarier the more we understand it. And honestly, if these cosmic monsters don't inspire you to keep learning about space, I don't know what will. So hit that subscribe button and like this video to help us keep exploring the scariest corners of the cosmos. Thanks for staring into the abyss with me, and I'll catch you in the next one.